Hello viewers, welcome to this series on heterocyclic compounds. In this series, we will study about different types of heterocyclic compounds and their importance in our life. Then we will study about the structure of different types of heterocyclic compounds, their methods of preparation and their chemical behavior. In today's session, we are going to have a quick look on the classification of heterocyclic compounds and their importance in our life. How important role they play in our life, we are going to look at that. After that, we will study about the structure of pyrrole. In pyrrole structures, we will discuss it in two ways. One according to the molecular orbital theory and secondly according to the valence bond theory, that is its molecular orbital structure and its valence bond structure that are also termed as resonance structures. And then we will study about the methods, different methods of synthesis of pyrrole and some important methods of synthesis of pyrrole derivatives. Now, first we are going to discuss introduction of heterocyclic compounds. A heterocyclic compound is one which contains a cyclic structure having at least two different kinds of atoms in the ring. In many cyclic compounds which you might have studied so far like benzene, naphthalene, phenols, benzaldehyde etc., the rings are made up of only carbon atoms. Such compounds are called homocyclic compounds. But there are a large number of compounds which are made up of rings containing, in addition to carbon atoms, other kinds of atoms also. Most common of them are nitrogen, oxygen, sulfur etc. Besides these, other metal atoms like silicon, beryllium, phosphorus are also there as heteroatom in the molecules. These are called heterocyclic compounds because hetero in Greek stands for different. Some examples are pyrrole, furane, thiophene, indole, quinoline and isoquinoline. Heterocyclic compounds are widely distributed in nature and are very essential to life in various ways. Chlorophyll, a green pigment of the leaves, it has heterocyclic rings containing nitrogen. It is very important compound for photosynthesis. Similarly, heme, red pigment in our blood, is also heterocyclic. It has heterocyclic rings containing nitrogen atom. You see that heme is very important in our life. It carries oxygen to different cells in our body. Nucleic acids, very important compounds in our body, RNA and DNA. They also have heterocyclic ring systems in them. Similarly, sugars, for example, which are very important ingredients in our food, they are also heterocyclic in nature. They have oxygen as the heteroatom in them. Vitamin C also has oxygen as the heteroatom. A large number of members of vitamin B group, they are also heterocyclic in nature. They have nitrogen in their ring. A number of alkaloids which are ingredients in the plants, they are also heterocyclic in nature. Not only these, but antibiotics, most of the antibiotics including penicillin is also heterocyclic in nature. So, there is a very important role of heterocyclic compounds in our body. On the basis of their characteristics, heterocyclic compounds can be divided into aliphatic or aromatic. Aliphatic heterocyclic compounds are those which has rings but are aliphatic in nature, while aromatic compounds are those whose rings possess aromatic characteristics. The most important and most interesting heterocyclic compounds are those that possess aromatic properties. So, we shall focus our attention to a few of them. Now, first we will start from the 5-membered heterocyclic compounds. Most simple heterocyclic compounds are pyrrole, furane and thiophene, are the simplest of the 5-membered heterocyclic compounds. Each of them contains a single heteroatom. Pyrrole contains nitrogen, furane oxygen and thiophene sulfur in its ring. On the basis of elemental analysis and molecular weight determination, molecular formula of these compounds are found to be C4H5N for pyrrole, C4H4O for furan and C4H4S for thiophene. X-ray analysis shows that they are planar molecules. These molecules have been assigned the following structures. Pyrrole has this structure, furan this one and thiophene this structure. Looking at these structures, one might expect that these compounds must show properties of a diene. That is, they should give addition reactions because there are two double bonds there, and besides addition reactions, pyrrole must show properties of a secondary amine, furan must show properties of an ether and thiophene properties of a thioether. But it is found that these compounds do not show these properties. They have very little tendency for these properties, that is for addition reactions. Rather than these compounds show electrophilic substitution reactions, which are properties of aromatic compounds. And just like nitration, sulfonation, halogenation, Friedel-Crafts acylation and alkylation. Besides these properties, they are so reactive that they give properties of aromatic compounds, of highly reactive aromatic compounds like amines and phenols, just like coupling with the diazonium salt or Reimer-Tiemann reactions, etc. When their resonance energies were calculated on the basis of their heats of combustion, it was found that these compounds possess high resonance energies in comparison to a diene. However, the resonance energies are somewhat lower than resonance energy of benzene, but they are much higher than the resonance energies of dienes. This also indicates that these compounds are aromatic in character. Even their NMR spectra show the ring currents, which is property of aromatic compounds. All these properties show that these compounds are aromatic in nature, and these structures are not the adequate representation of these compounds. On the basis of these properties, that is why pyrrole, furan and thiophene must be considered aromatic. So, it is clear that these structures are not the proper representations of these compounds. Now, molecular orbital structure of pyrrole. As the microwave studies have shown that pyrrole molecule is completely planar. All the 4 carbon atoms and the nitrogen atom in pyrrole ring are sp2 hybridized. In the excited state, the pyrrole atom has this type of electronic configuration. That is, one of the electron from 2s orbital has jumped to the vacant 2p z orbital of the carbon atom. Then one s orbital and 2p orbitals of carbon, they combine together and get hybridized to give 3 sp2 hybrid orbitals. These sp2 hybrid orbitals are planar, they are planar triangular in structure, in their geometry, inclined at an angle of 120 degree. Now, there remains one pure pz orbital, which is unhybridized orbital, which is in the plane perpendicular to the plane of these 3 sp2 hybrid orbitals, and this pure p orbital also has a single electron in it. Nitrogen is also sp2 hybridized. In its excited state, one electron from 2s orbital of the nitrogen jumps to the pz orbital, and then the 3 orbitals, each having one electron, one 2s orbital and 2 2p orbitals, they combine together to give 3 sp2 hybrid orbitals, while the pure pz orbital, which is in the plane perpendicular to the plane of these hybrid orbitals, has a pair of electrons, not only a single electron unlike the carbon atom, but it has a pair of electrons in it. Now, out of 3 sp2 hybrid orbitals of carbon atom, 2 are involved in the ring formation by forming sigma bond with the neighboring carbon atom by overlapping sp2 hybrid orbital of the carbon atom or sp2 hybrid orbital of the nitrogen atom. And the third one is involved in the bond formation, sigma bond formation with s orbital of hydrogen atom. So, all the 3 sp2 orbitals of the carbon atoms as well as of nitrogen atom are involved in sigma bond formation. sp2 orbitals of nitrogen atom out of these 3, 2 are forming sigma bond with neighboring carbon atoms, while one is forming a sigma bond with by overlapping s orbital of hydrogen atom. Now, after this, as we know that all the sp2 orbitals are in the same plane, that is why the 4 carbon atoms and the nitrogen atom including hydrogen atoms are in a single plane. Now, there is one pure p orbital on each atom of the ring, on each carbon atom and on the nitrogen atom, and these pure p orbitals are in a perpendicular plane to the plane of the ring. P orbital of the carbon atom, each carbon atom has 1 electron as we have already studied, and p orbital of nitrogen atom has 2 electrons on it. These orbitals overlap each other and form a ring pi electron cloud over and below the ring of the compound. Now, this pi electron cloud, as we know, have total number of electrons is 6. That is, it is making pi electron 6 sextate, which is according to Haeckel's rule is the characteristic of an aromatic compound. This shows that pyrrole is aromatic in nature because it has an aromatic sextate there. So, according to Haeckel's 4n plus 2 pi electron rule, because of the presence of these 6 delocalized pi electrons, pyrrole is more stable in comparison to a conjugated diene and it shows aromaticity. Now, because carbon atom in this case the total number of electrons is 6 and these 6 electrons are distributed over 5 atoms and every carbon atom is contributing only 1 electron. That is why the total negative charge on every carbon atom is greater than unit, while in case of benzene the negative charge is unit on every carbon atom, because there are 6 carbon atoms and all are contributing 1 electron, that is total number of electrons is 6, while in this case the total number of electrons is 6, but the number of atoms on which these 6 atoms are there, it is 5. That is why the total negative charge on each carbon atom is greater than the negative charge on the benzene nucleus, and that is the reason that pyrrole is more reactive towards electrophilic substitution reactions in comparison to benzene, because its electron density on every carbon is greater than that. And because of this high reactivity towards electrophilic substitution reactions, it undergoes reactions like coupling with diazonium salts, which are given only by most reactive benzene derivatives like phenols and amines. Further, as we know that the basicity of amines is due to the presence of lone pair of electrons on the nitrogen atom, and in pyrrole ring this electron pair is contributed towards the pi electron cloud forming aromatic sextate. Therefore, unlike amines, pyrrole has very little basic character. So, its aromatic character and little basicity can be confirmed on the basis of its molecular orbital diagram. Now, we can also explain its aromatic nature on the basis of valence bond theory by studying its resonance structures. On the basis of valence bond theory, pyrrole is actually a resonance hybrid of these 5 canonical forms, 5 resonance structures. As there are 2 electrons on the nitrogen atom, they are contributing towards this pi electron cloud. So, there is a slight positive charge on the nitrogen atom and slight negative charge, extra negative charge on the carbon atoms. So, there are these 5 resonance structures which are contributing towards the resonance hybrid. This is the actual structure of pyrrole, it is supposed to be the actual structure of pyrrole, which we call as resonance hybrid structure of pyrrole. Now, excepting one, all the other structures have charge separation. That is why these structures are somewhat less stable in comparison to this first structure, which does not have any charge separation there, and that is why it is this structure which contributes most to the resonance hybrid structure of pyrrole. Now, you might have studied that in benzene there are 2 such structures in which there is no charge separation, that is Kekulé structures, which are more stable in comparison to other canonical forms. So, as in benzene there are 2 more stable structures which are contributing to the resonance hybrid of benzene, while in pyrrole there is only one structure there. That is why pyrrole is more reactive in comparison to benzene, and its resonance energy is less in comparison to benzene. Now, this hybrid structure of pyrrole has been supported by its microwave studies, which shows that pyrrole is a planar molecule. The carbon nitrogen bond length is found to be about 1.38 angstrom units, which is shorter than carbon nitrogen single bond length, and carbon carbon double bond lengths are also shorter than carbon carbon single bond lengths and longer than carbon carbon double bond lengths. As this diagram is indicating that these bond lengths are, although all the bonds are not of equal length, but all these bonds are slightly shorter than carbon carbon single bond and similarly carbon nitrogen single bond, while they are slightly longer than carbon carbon double bond and carbon nitrogen double bond. So, we can say that all these bonds have partial double bond character, which is confirmed on the basis of its resonance structures, because in its various resonance structures all the bonds are slightly double bond. This hybrid structure of pyrrole is further supported by its dipole moment, its ultraviolet and NMR spectral studies. Now, we will see some methods of synthesis of pyrrole. There are a number of methods with which pyrrole can be synthesized. Some methods are laboratory methods, while others are commercial methods. In laboratory, pyrrole can be synthesized by following methods. From acetylene, we can prepare pyrrole in laboratory from acetylene in two ways. Number one, when a mixture of acetylene and ammonia is passed through a red hot tube, pyrrole is formed. The reaction, according to this reaction, the ratio is 2:1, ratio of acetylene to ammonia is 2:1. When this mixture is passed through a red hot tube, we get pyrrole and hydrogen is eliminated out. In the second method, acetylene when treated with formaldehyde in presence of copper carbide, we get an intermediate but-2-wine-1,4 diol, which under pressure reacts with ammonia to give pyrrole. This is also used in the laboratory. Another laboratory method for the synthesis of pyrrole is from ammonium mucate. It is a very good method for synthesis of pyrrole. In this method, pyrrole can be obtained by heating ammonium mucate with glycerol at about 200 degrees Celsius or about 473 Kelvin. It is believed that under these circumstances, ammonium mucate first dissociates into the free acid and then it undergoes dehydration and decarboxylation, and then it reacts with ammonia because ammonia is liberated here. It has been dissociated into free acid, that is why ammonia has been liberated. So, it reacts then with ammonia to give the pyrrole. Pyrrole can also be synthesized from succinimide. When succinimide is distilled with zinc dust, it gives pyrrole. On a large scale, on a commercial scale, although generally pyrrole is obtained by distillation of bone oil, but it can also be manufactured by passing a mixture of ammonia, furane and steam over heated alumina at about 500 degrees centigrade or 750 to 763 Kelvin. When furane and ammonia are passed over heated alumina, then pyrrole is obtained. Now, we will study some important methods of synthesis of derivatives of pyrrole. First, Hensch pyrrole synthesis. In this reaction, an alpha haloketone is condensed with a beta ketoester in the presence of ammonia or a primary amine. We can take either ammonia or any primary amine according to the requirement. This is the scheme of the reaction, that is alpha haloketone condenses with a beta ketoester, for example acetoacetic ester, or it may be some other derivative of acetoacetic ester, and then in the presence of ammonia or primary amine, where R may be methyl, ethyl, isopropyl or any other alkyl group, they condense together to give first this intermediate and then the final product, which is a derivative of pyrrole. Pyrrole derivatives can also be synthesized by another very important method, Nor-pyrrole method or Nor-pyrrole synthesis it is termed as. This is the most commonly employed method for the synthesis of pyrrole derivatives. This method involves condensation of an alpha amino carbonyl compound, or it may be alpha amino carbonyl ester with the beta ketoester in the presence of acetic acid. The reaction scheme is this one, that is, in this case we have taken alpha amino carbonyl compound with a beta ketoester to give derivative of pyrrole. One another method for the synthesis of pyrrole derivatives is Pal-Knorr synthesis. In this method, an ionizable diketone, generally 1,4-diketone, is treated with either ammonia, or even ammonium carbonate may also be taken here, or a primary amine, or hydrazine, etc. When all these get together, they condense together to give the pyrrole derivative like this. This is the scheme of the method. The ketone, this diketone, it is 1,4-diketone. This diketone should be enolizable, that is, it can be converted into an enol, then only it will work in this method. So, these are some important methods for the synthesis of pyrrole derivatives, and we also went through the synthesis of pyrrole itself. So, today we discussed about heterocyclic compounds. We took its introduction, that is classification of heterocyclic compounds, their importance in our life, and then we studied structure of pyrrole as well as resonance structures of pyrrole, and how these structures prove that pyrrole is aromatic. It is not aliphatic, but aromatic in nature. And then we studied the methods, different methods of synthesis of pyrrole, and some important methods of synthesis of pyrrole derivatives. In our next session, we will study about structures of furane and thiophene, and then we will discuss their chemical behavior of all these compounds, that is pyrrole, furane and thiophene, and we will also discuss structure of pyridine in our next session.